Been doing it since 2012.
Okay,
I think so.
in principle,
many.
in the past was twice a year too, right?
Yes.
So I don't know. We lost count.
24th, maybe.
I think we were very visionary, I would say, and
Yeah.
courageous to
When we
jump
started.
into quantum biology and quantum medicine. Now it's becoming popular. It's popular in the sense of lay audience, from technical. You know, when I first got exposed to quantum biology about that time, I was invited to a conference in India at Indian Institute of Technology, and they wanted to create a quantum biology course. And I said, forget about it, it's impossible, it's just too hard.
Right.
Too many moving parts, biology, physics, biochemistry, nobody can do this. And they said, no, we get about 1 million applicants from students all over India, and we select the best 100, so they will be. This may have been an exaggeration, but so this is a 4-lecture series, which covers a lot of territory, and there's a lot of these lectures on YouTube. So I want to mix things up a bit and shake it up. It'll be a little bit different, and also in view of some recent developments, as I'll explain to you in a minute.
Cool.
But the topic is still the same. It's the topic is basically how you bridge the 124-year gap between physics and biology, medicine maybe another 20 years or less if we're lucky. From quantum physics to quantum biology and maybe quantum medicine, I use the psi, which is a wave function symbol. The Greek letter psi in quantum physics represents the wave function that we'll be talking about. And I also used the so-called Dirac notation here, which is the overlap between the wave function of physics and oncology. I spent 15 years in oncology. And I forgot to add one more. It's called the bracket, bra and ket, two quantum mechanical symbols that Nobel Prize winning English physicist Paul Adrian Dirac introduced to simplify, instead of all the mathematical psi of x, y, z, t, etc. Just this simple. And the other one is the complex conjugate of this function. And when you put them together, it's an overlap, which is basically an integral over the product of these functions. So kind of inside joke, I guess, for physicists or people who know physics. But there's another bracket that I did not include here, which is U of A and Politecnico di Torino in Italy, where I spent about half of my time, hopefully more. But anyway, that's the very short introduction. I also want to mention books which I co-authored on aspects of it, nano-neuroscience, because we'll be going deep and then zooming out of it. So first we'll go deep and then we'll zoom out. As deep as physics, of course, goes much deeper. Subatomic particles, Higgs bosons, and unimaginably small objects. For the sake of biology, as I will mention later, we'll talk about the scales and all that. For the sake of biology, nano is more or less where we should begin. Anything below nano is ho-hum. I think we don't know yet. Maybe important, but at the moment, not much. And then these two books, which kind of, I have to say, I was kind of reluctantly drawn into the field of the science of consciousness. This is a topic that kind of borders on science, philosophy, even spirituality, religion. You know, a lot of different actors in the field play different roles, and I represent, I would say, a very nuts and bolts approach as a very hard-nosed physicist. I don't buy things without checking around and very closely looking at them. So I was reluctantly drawn into this field because people were talking a lot about quantum this and quantum that. And you know, if you're another physicist, well, you know, you should talk to a physicist first before you say things like that. And at any rate, this book was published, the middle one, Emerging Physics of Consciousness. It was emerging in 2006 and became quite popular. And then there was a follow-up later on. And this is the most recent development, and that's why I'll be a bit more chatty, because I realized recently that this topic can attract a big lay audience, and Kim is responsible for me realizing this, because this course launched me into the YouTube sphere. I wasn't into that at all, and because of this course, my YouTube videos were posted from this lecture, and this will be, I presume, as well.
Yes.
And that led to some unexpected encounters, and I'm sure you experienced that too. People from all over the world ask you some questions and invite you here and there. In fact, 2 days ago, I got an email from the editor of the Hindustan Times
Wow.
in India, New Delhi, about some of this. Okay. I said, yeah, I can respond to your email. Yes, it's amazing. It is amazing. The world has shrunk incredibly.
Yeah.
So this led to this book, which now came out December 5th, 2023, so only about a month and a half ago. This is a book that I co-authored with Deepak Chopra. Some of you may know him. He's a public figure, I would say spiritual figure. And the book kind of melds together 3 streams, because the third author is a medical doctor and endocrinologist, Brian Fertig, who actually contacted me, had contacted me prior to this, several years prior to that, because of the YouTube video that was posted. And we collaborated for about 5-6 years on his 2 books on metabolism, which also speak about quantum metabolism that I'll be talking about. So that collaboration resulted in a popular book that you can purchase. I'm not selling anything. I have 1 copy for you, signed with a dedication, but I'll bring that copy on Tuesday because I owe you so much.
Yeah, great.
And I'll say a few things about this book to start the sort of to charge your imagination a bit, because this topic is as I say, at the intersection of several fields, including medicine, and hopefully medicine will benefit one day, perhaps not yet, but Brian Fertig, who's an endocrinologist, and Deepak Chopra, who's also a medical doctor, trained in also endocrinology. They are very enthusiastic, otherwise they wouldn't be writing a book like that, about the future of medicine. And so it fits into this course. But
it does.
So that's actually, I will say a few words about what this book started as and evolved into something else for various reasons. But since you're academics, I can delve a little bit deeper. The book doesn't cover these topics so much in detail, scientifically or otherwise. So kind of the organization of, as I said, 3 streams, and the first stream is more about the mysteries of life. You know, we still don't have a very good definition of what life is, let alone what consciousness is. And consciousness will be the topic of the last part of the course. The 4th lecture probably will be on topics related to the mind and the brain and the mind, neuroscience, consciousness, all these topics that I think everybody thinks about, but very few people are brave enough to say anything, especially scientists. You know, they are not brave enough to say anything about consciousness because they can be criticized too easily, myself included, but now I don't have too much to lose. I don't care. Just like Rick Gervais at the Oscars, you know.
Yeah.
I don't know if you saw that. No? Yeah. Go to YouTube. Rick Gervais, the comedian from the UK. He had a very funny speech at the Oscars a few years ago. It was his last performance. I said, I don't care. I can tell you what I think. So I will try to tell you what I think about consciousness later on. But we need to build, you know, you can say anything, but unless you provide the framework and the background, that becomes kind of funny and ridiculous sometimes. So I will say things a bit later with maybe more conviction and more common understanding of these topics. Anyway, so the first aspects of this topic, this book, are incredible synchronization and organizational perfection of all living systems, especially the human body. When it works perfectly, it's a mystery how it does so. And you know, people can bring in anatomy and physiology and biochemistry. You can explain more or less every piece at a time of this puzzle, but the entire puzzle as a whole is not explained, in my opinion. Nobody can explain to you the synchronization of all the activities that we're performing, and in particular, the mysteries of the brain, how it can integrate. I'll talk about this a bit later, which is, by the way, something I want to write about in another book after this one. The integration of all the sensory inputs into a coherent and synchronized image of the world around you, you know, albeit with very narrow band of inputs in terms of frequencies and resolution and all that, but we still perceive the world as one, and we don't have a separate view through sound, a separate view through vision, separate view through tactile inputs, etc. It's all integrated and coming together at once, and we see it as a three-dimensional movie, let's say. Some people call it the theater of the brain, or the mind, theater of the mind. It is kind of, but where is this? Is this happening inside the brain? Is there a little screen? Nobody has seen such a thing, but this is how we see it. Okay, so self-organization, who is in control of it? Everything seems to be self-organized, spontaneous, and so there isn't nobody in charge really, but we know that we have some volition. Some people actually contest the concept of free will. I don't know if you ever thought about this. There's some recent Professor Sapolsky from Stanford. I think he's a very famous Sapolsky, I think is his name, famous biologist, evolutionary biologist, and he claims very powerful that we don't have free will. I completely disagree with this. And I think there's an ancient proof of that. You know, a philosopher kicked a stone and said, that's the proof. So you can just do whatever you want, but I understand that our actions are limited by many things, genetics, conditions, environment, pressures, etc., etc. So it's not complete free will. You know, I cannot do whatever I want, but I can do a lot of things that I really want to do, and nobody will stop me. Anyway, so that's this topic of who's minding the star. I mean, there is the, and I think free will, by the way, we'll come to it maybe later, in my opinion, an expression of free will or deliberate motion, performing a deliberate movement, not by external forces, but by internal willpower, if you will, if you want. So deliberate movement is characteristic of living systems. Inanimate matter cannot do that. It just does what the forces around tell the object to do, whether it be a stone rolling down a hill due to gravity, or ocean waves due to wind pressure and you know, movement of the earth with respect to the moon, etc., etc. You can always find an external source of movement, but then when you look at even bacteria, they decide, you know, where to tumble and where to move forward, you know, and let alone our own behavior. Okay, so then there is something about the Goldilocks zone, which, and by the way, many of these topics you can find that we wrote little snippets on the internet. There are some essays, and there are also some YouTube videos that Deepak Chopra is posting every day, by the way. He has a channel called the Chopra Well, Deepak Chopra Well, maybe. The Chopra Well, I think it's called. TCW. And every day you'll find about 10 minutes, 15 minutes sometimes less, of his deliberations, ruminations, monologues on these topics. So, order out of chaos. That's another thing. In biology, this is actually one of the first real serious doubts that physicists expressed, in particular Erwin Schrödinger, Nobel Prize-winning physicist who actually came up with this science, the wave function, expressed in regard to order. Biological systems all create order, either structural and or actually dynamical, functional order. And that's, in the language of physics, entropy reduction. So there's no biological system that does not perform entropy reduction. And Schrödinger wrote a book about what is life, whose main theme was entropy reduction, which is against the well-known second law of thermodynamics expressed by Stefan Boltzmann at the end of 19th century. And so that's only seemingly contradictory to the second law of thermodynamics. The second law of thermodynamics doesn't say anything about open systems like we are. I'm breathing, exhaling, inhaling, interacting, the molecules come in and out of my body. And that's number one. Number two is out of thermodynamic equilibrium. That's a concept in physics. Thermodynamic equilibrium, that means a stable state that is reached asymptotically by a physical system. Let's say a sand pile eventually crumbles down and levels with the rest of the beach, more or less. Biological systems are far from equilibrium. That's the nature of our being alive. So order out of chaos. So chaos meaning the external turbulence around us, and biological systems are able to retrieve molecules and sources of energy and some other molecules, catalysts, for all of this, to create order. And that's how does it happen? What's the trigger, and so on. Then there is a little bit about symmetry is part of that. Symmetrical systems are ordered, so there's creation of symmetry. And there's another interesting field of physics that I would like to maybe expound on someday with repercussions on it. It's called the physics of phase transitions, or critical phenomena. Because neither quantum mechanics nor classical mechanics per se speak about phase transitions. Phase transitions are transitions between phases of matter. Things like water freezing into ice or boiling into vapor and so on. This is a phase transition. And every phase transition, by and large, by the way, this is a popular thought. I know that physicists will jump on me, oh yeah, but there's an exception. Yeah, I know that. But I don't want to muddy the waters with too much detail. So every phase transition, by and large, is related to a so-called broken symmetry, a change of symmetry of the system. There is some symmetry which is gained or lost, depending on which way you go. So in the case of ice, you have translational symmetry. That means water molecules are ordered more or less periodically. But when it goes into water molecules have the freedom to move around, and they have complete symmetry, rotational and translational, which is lost in ice. So it's symmetry breaking. That's the concept of symmetry breaking. By the same token, when you talk about living systems as opposed to non-living systems, there is a broken symmetry. Namely, living systems have some sort of directionality. For example, functional typically. For example, if you look at a living plant as opposed to a just dead plant, then you'll see the fluxes of water and carbon dioxide and oxygen, carbon dioxide in, oxygen out. These fluxes are symmetries because they have directions. When the plant dies, this is gone. There is no flux. So that's one of the symmetries which is broken, directionality of movement of something. Okay, so I hope you learned something already.
Yes.
And I think, so just another comment, Brian Fertig, who is a practicing medical doctor with a very big practice in New Jersey, he strongly believes that medical education, in North America at least, I think in elsewhere as well, would benefit tremendously from physical insights, because we, as physicists, we simplify things, sometimes too much, but quite often this simplifying point of view clears up some issues, let's put it this way. So, okay, search for meaning, that's a bit more philosophical. What is the meaning of living systems? I think, in one word, the meaning of life is to live. 2 words. I was once in, I spent a year in Brussels, Belgium, and I was obsessed with this topic, the meaning of life, and I remember taking a bus in the center of Brussels, and there was an art exhibit called The Meaning of Life. I said, okay, that's what a coincidence, you know, I'm thinking about this, and this is, and this is there, okay. The answer is trivial, I guess, although there may be, everybody has a slightly different point of view about this. But I think everybody searches for some kind of meaning. Meaningless life is probably not worth living, but that's only me saying that. And then there is a lot of more technical aspects. I will just pick a few to discuss the concepts. One of which is stress response, which leads to, according to Brian Fertig, to a revolutionary idea in medicine. And I would like to hear your opinion, Kim, and maybe anybody else who is a medical student, maybe. Namely, stress test is known in cardiology, right? So which means you try to determine the physiological response of a patient subjected to physical exercise, walking an inclined treadmill, and increasing the angle and seeing at which point the person will stop or will have a very high heart rate. So it's basically heart rate versus the stress, physical stress. Right? And I think this illustrates the point that this is more or less unique in medicine, because we feel that in medicine there should be more stress tests in different fields as well. Anything that disturbs the system slightly out of equilibrium and tells you how the system, the biological system, responds to stress, whether it be psychological stress, you know, maybe students experience stress at exams and monitoring the heart rate, you know, so, and then return to equilibrium, how long it takes to return to equilibrium following a stress. So if the system is strong, it will withstand a very large amount of stress. Let's say weightlifting, you know, some muscle and so on. If the system is, and also returns rapidly to equilibrium. If the system is weak, actual stress will not only cause sometimes a temporary heart palpitation, you know, disturbance, let's say, not just a faster heart rate, but maybe some fibrillation, but it could actually take you to the next, what we call allostatic overload, the next stability zone. So prolonged stress, let's say even low level stress, can cause a pathological change. You know, you may become so depressed, or you may become diabetic, or some other condition may emerge as a result of prolonged stress. So that's this concept of, we call it physiological fitness landscape. So mapping responses of the human body to different factors, including pharmacological. That'll be another. If you want to test if this drug works on somebody, you dose escalate, you know, it's small dose, no effect, and a little bit more, yes, you know, blood pressure is going down, and eventually, of course, the huge dose would kill, but we don't want to go there. We just want to see the curve. In physics, it's usually called the free energy landscape. So how the free energy changes as a result of the we call this a control parameter. Control parameter is the stressor. Stress, and it goes back actually to the very first, almost very first experiment in physics by Robert Hooke at Oxford University in early 1700s. Springs, so you apply a force, extend a spring, and then returns to its original length. But if the force is very, very large, you can distort the spring, it never returns back, or even breaks, right? So this is the same concept, to try to and find human responses to such things. And when you do this, you plot the stress-strain. Strain is the outcome of applying stress, change in some parameters, stress-strain relationship. In the case of Hookean springs, Hooke's springs, linear spring is a straight line. But eventually it curves and saturates. So from this you can create the free energy function. Okay, I don't want to get into technical details. I hope you get the idea. The stress tests is something that maybe we should be introducing on a larger scale than just in cardiology. I know that if the system gets too stressed, it may, and this actually brings us to quantum mechanics, it may deform the system beyond repair. In other words, I think doctors would be very Hippocratic oath. You don't want to damage the health of the patient. And if you overdose on some drug medication, the patient may experience a heart attack. For example, there were some cases of, quite often actually, it's maybe not reported, clinical trials, right? In clinical trials, healthy volunteers typically would be given some medication to test their response. And this was hepatitis C drugs by Bristol Myers Squibb, tested in about 10 years ago. They actually caused heart attacks in several volunteers. One passed away. So this is a stress test taken too far. We don't want that, right? But if you titrate carefully, you will be able to see how that response changes. And from the response, you can create a landscape. It could be multidimensional. So we call it physiological fitness landscape. So stress response. Friend or foe. Is stress a friend or foe? And again, there's this famous saying, Nietzsche's, whatever doesn't kill you makes you stronger, right? I'm not quite sure it's quite correct. It's not always that it makes you stronger. It could make you weaker too, even without killing. and I mean, of course, anecdotal evidence is all around us. Some people get so stressed out. I can give you one anecdote. One of my students, who didn't have the background in physics, but was enrolled in physics, the Department of Physics, at my insistence. No, he almost gave up on science because one of the courses was so stressful he couldn't cope, and he was in tears. I said, just drop it. We'll find something else. And then so we prevented this this catastrophe, which would kill the person, but it would kill his scientific career. He's now a professor actually at a university in Canada. So everything is fine. But it's not okay. So now we have this. This more or less is what I would like to delve deeper into from that menu. It's organized into 12 chapters. A brief history of quantum physics. So quantum physics. If you take physics, I presume nobody here is enrolled in physics. Even Jacopo, he's in biomedical engineering. You would take at least 3 undergraduate one semester courses in quantum physics, and at the graduate level, at least 1 or 2 more. So it's, let's say, at least 2 years of studying quantum physics. I'll try to cover this in the next 50 minutes. Maybe not cover, but give you a taste of this bitter medicine. And then we will, in the next, so on Tuesday, the next lecture, we'll talk about how can we use these ideas in biology to begin with. Is it even possible? Are there any examples of quantum effects in biological systems, living systems? And then I'll build on that and go into some more detail in the third lecture, and the last one will be all about neuroscience, the mind, you know, and maybe glimpses of consciousness, which is the most mysterious aspect of neuroscience. Nobody is the wiser.
Maybe I'll
Okay.
just say one thing so that you guys don't get terribly stressed out about this. That the midterm is open book. So you can, you know, access the internet,
Open everything.
Yes, totally open. And in fact, part of the midterm, Shauna Pandya's part, requires the use of Chat GPT. So it's not that you might want to use it, but you actually have to use it for her part. So the course is not much about memorizing things, and it's not about formulas. And
No
It's
equations.
sort of about the big picture. So I think this will allow you to relax more in this kind of lecture. Holy smokes, how am I gonna, be able to regurgitate this? You don't have to. So,
Yeah. I mean, this is multidisciplinary in its, it's par excellence. It's really so many disciplines bearing on it, and not just physics.
Yeah.
So I don't expect you to understand every word I say, but I expect you to get the gist of it, and we'll get into what the gist is. And for example, there might be a question, what is the main difference between classical physics and quantum physics? And that really you could cover it in one sentence, as I'll show you. Okay. And then, there's some applications of quantum biology to health and disease. I think the most exciting and the most possibly transformative advances would be, if somebody here is watching me, is a psychologist in psychology and psychiatry, because this, our states of mind are like quantum states in a physical systems. You can be in a superposition. You may be looking at me thinking about your boyfriend or the next week's exam or something like this, right? So you have superposition of different mental states. And then, of course, I ask you a question and you have to respond to it, and then this mental state collapses on the answer, or sometimes you just talk to yourself and you collapse the mental state. Another thing would be, in quantum physics, is the so-called non-commutability. That is, the order of things matters. Let's say if you ask the first question about maybe your a personal question about yourself, and then the second professional question, or vice versa, you may give different answers depending on how I order the questions. This is just a trivial example. Think about it. Many such cases. So psychology, in my opinion, satisfies many of the prerequisites for quantum systems. And another one is, of course, if you go beyond a single person, but two people who are, let's say, emotionally connected. In quantum physics, you'll call it entangled. States are entangled. So the state of your mind may be affected by the state of mind of your significant other, or your parents. There is an influence. But if it's somebody that you are not entangled with, a person from the street, maybe in distress, you'd be probably sympathetic, but this will not have the same emotional effect as somebody close to you. Okay, so this is a lot of similarities, even states of excitation. In quantum physics, we use the term excited ground state, which is you just wake up. Okay, it's a ground state. That's the baseline, and then you turn on the news and there's, you won $1 million in the lottery, and your excitement goes through the roof, right? So you get into an excited state. In physics, that's exactly true as well. You can get into several excited states or an infinity of excited states in some cases. And anyway, so psychology, psychiatry, and psychiatry also would benefit because of things like schizophrenia or, you know, distorted perception of outer reality in mental states. Again, in quantum mechanics, in modern quantum physics, there is something called Q-deformed states. So these commutation relations change. There's a knob, a dial. You can go from quantum to classical through deformed states. Anyway, for now it's just blah, blah, blah. You know, I'm talking, you're listening, and maybe not really I'm not communicating very well, but you'll get to that. And this is the last, which is an unwritten book. A book that I want to write about, kind of a title that is working title called Between the Classical Brain and the Quantum Mind. So classical brain is neuroscience, you know, basis of neuroscience, you know, the brain, the neurons, synaptic connection, neurotransmitters, and all that. But there is something mysterious emerging out of all of this. There's of course neurophysiology, electrical currents, action potentials, traveling at speeds of, let's say, a meter per second or something like that. But then you have things like a flash of genius, and not some insight, intuition, premonition, feats of athleticism, you know, which cannot be explained by normal physiology, so they can be probably explained by something else, like quantum effects in the brain, which connect the brain parts of the brain instantaneously almost. They get entangled, like in quantum physics systems get entangled. There is no domino-like effect. You know, in classical physics, people typically think about billiard balls colliding, you know, and dominoes falling. These are mechanistic, very simple-minded approaches. Quantum physics is quite different. Systems are connected in an integral entity through their overlapping wave functions. They are holding hands, you know, all the time, and interaction can be transmitted over arbitrary distances instantaneously. So that's where I think some of the exotic things emerge. So quantum states of the brain. Is brain a classical quantum computer? Now we talk about quantum computing. Quantum computing is a reality. We achieved quantum computing after how many years of human civilization? 10,000, something like this? Compared to 2 billion years of life on this planet, this is nothing. It's an instant. Why wouldn't life develop quantum computing in the brain by trial and error? You know, and we can do it by, you know, tinkering with silicon or photons or things of this nature, right? So there's compelling evidence that living systems, by nature's design and Darwin's laws of competition and natural selection, perfected themselves to acquire a lot of properties which we only now grasp through our intellect. Okay, so yeah, and then there's some aspects of psychiatry, neurodegenerative diseases, what happens when things go awry, you know, what parts do not work, where there is disconnect, where things may, I would say, go from quantum to classical. Quantum, to me, and also if you listen to Deepak Chopra's YouTube videos, is more or less like perfection of design and execution of function. Classical is this, you know, inefficient, domino-like, step-by-step, brute force. That's the difference. Okay, so this was a longish introduction that I hopefully gave you my personal perspective on things, and now we'll go a little bit into the details. By the way, this whole field of quantum consciousness or quantum mind or even quantum biology was largely launched or affected by Sir Roger Penrose, who wrote this book, The Emperor's New Mind. I think it was about 30 years ago, 1992, maybe a bit later, I don't remember exactly. Actually, I was given a copy of this book by Roger Penrose before he published it, and was asked to comment. It's an amazing, very hard book to read, but it's an amazing piece of scientific literature. Roger Penrose got a Nobel Prize in Physics in 2020, so it's now 4 years ago. He's one of the greatest physicists of 20th century and 21st now, and maybe the greatest alive. And he also addressed a lot of the topics that I'm trying to understand, but of course, I'm not comparing myself to him. I'm just a humble, as I said, nuts and bolts biophysicist. So anyway, I highly recommend this book, and there's a second book, Shadows of the Mind, I think it's called, that follow it. And these became bestsellers, but moved the needle in terms of scientific discourse. And so in the last 120 years, we can say that in the year 1899, or late 19th century, there was an overwhelming conviction among the physicists and scientists in general. Physics is finished. We've done everything that can be done. Right? That was the overwhelming feeling. The rest is engineering, technology, improvements, optimization, but all the laws of physics are known. Let's move on. And then in the year 1900, everything collapsed and everything changed. And that was the birth of quantum mechanics, in addition to other revolutions. So this was the decade of scientific revolutions in physics. Relativity by Einstein, quantum physics, mechanics, they called it then, by several people, Schrödinger, Heisenberg, Einstein also contributed. But what I want to say is that quantum physics was a true scientific revolution that occurred rapidly, and only as a result of maybe 5 or 6 experiments that physicists couldn't explain at that time using classical concepts. And I think in biology we can number these experiments of facts that are troubling and we cannot explain. One of which is, of course, the enigma of consciousness, and there are some other ones, the synchronization, organization, imperfection, and so on. For me, there's another one which some people would call an easy problem, but I think it's very difficult, is how sensory inputs through receptors, molecular receptors, which many of them for sure act on quantum principles by binding a single molecule and changing its state, conformational state of the enzyme of a protein receptor, trigger physiological macroscopic response. So amplification of signals in the face of overwhelming thermal noise and general noise, to me is one of those unexplained phenomena. I'm trying to remember the book, Werner Lowenstein wrote a book about this kind of thing. I'll maybe recall the name of the title of the book later. But so there are a lot of such things. One of those technical aspects which people couldn't explain for many years was protein folding. And this was expressed as a so-called Levinthal's paradox. So you take a single protein and unravel it to basically turn it into a peptide chain, polypeptide chain, and then you let it fold again as a result of hydrogen bonds and hydrophobic forces and so on. So based on the calculation of how many states the polypeptide chain would have to explore, Levinthal calculated, would take the age of the universe by brute force to find the conformational state of the folded protein. If you do these experiments in the wet lab, the protein folds in a matter of milliseconds or less. So obviously, there are some people claim, well, that's various explanations now, and some people claim it's a result of quantum search algorithms that the molecule.
So this is one of the things in the course that has been most heavily discussed. The first time that Jack talked about this and said it was very likely done through quantum algorithms just happened to be around the time that the activity around AlphaFold was sort of ramping up, you know? And when that great success was made, people concluded, well, it's not quantum at all, you know, it's
No,
entirely.
I don't think it solved the problem.
No,
No, it hasn't.
no.
Because AlphaFold operates on a database of known cases. It's a pattern recognition.
Right. Yeah.
But this molecule doesn't have a computer that recognizes patterns
No.
in many
No.
other products.
No.
It just does it.
So it's much more of an open question. So when you talk to somebody who believes that they completely understand protein folding, you realize that person's wrong. That basically the human brain cannot conceptualize the way proteins fold. I mean, AlphaFold was a major advance in allowing us to kind of, you know, predict this.
Yeah.
But we still don't really know how.
No, and AlphaFold doesn't explain anything, it just gives you answers, right?
Right, yeah.
It's like
Yeah.
Chat GPT.
Yes,
Gives you answers, but you know, there's no, in fact, that's another long conversation. Roger Penrose, when you asked him about the difference between AI and human mind,
Right.
he says, we know things. The computer doesn't know anything. It just searches for patterns and puts together some work. They may be reasonably phrased, I'm not disputing that, but there's no knowledge. It's just pattern recognition and formation of patterns out of.
Yeah, but there's a pride of being human that's an easy trap to fall into.
Hubris.
Yeah, the more advances computer make, you think inside yourself, well, I'm human and bound to be things computers can't do. And it's so satisfying to believe that, but there's actually nothing supporting it except your wish for it to be true. But there are lots of other things you believe because you wish it to be true, right? I mean,
Well, yes, and no, I will, I mean, we're getting into the nitty-gritty of these arguments. We'll come back maybe at the last lecture, but Roger Penrose gives examples that a computer cannot solve problems because it's organized algorithmically that we can easily solve just by looking at them. And for example, I mean, there are some other strange effects, let alone, you know, emotional states that computers don't have. You know, they don't fall in love, or they don't hate anything or love anything. That's separate. But sometimes you walk down the street and you feel that somebody is watching you from behind, right?
Right.
I don't know if you experience this.
Yes.
Quite often, right?
Yeah.
Extrasensory perception or something like that. Or, you know, insights, sudden insights.
Right.
Computers don't have sudden insight. They just follow some algorithm. So non-algorithmic thinking is what this book is arguing.
Right, but it's not a static system. You know, human culture is evolving and computers also are. So you can't claim that
Well,
they'll never be able.
I know.
Right? Yeah.
You're telling me that they're catching up with us.
Yes.
Yeah.
That's what I'm saying.
For sure.
Yeah.
And I don't want to play chess with a computer. I'll lose in 5 moves or something.
Right.
Okay. So, but coming back to the history of science, so 300 years of classical physics from about 1600 to 1900 until today, quantum physics, sudden revolution in the space of 20 years, 2 decades or so. And then quantum chemistry, it's a very quick jump from physics to chemistry, all chemical, pretty much all chemical bonds. Again, if chemists are here, we can talk about this, but are quantum in nature because they involve sharing or exchanging electrons, and these are quantum particles. There are some other bonds as well, I know, but okay, by and large, all chemistry is quantum. Okay, you wouldn't have, first of all, and we'll come to it, you wouldn't have even atoms without quantum physics. And for sure, you couldn't have molecules without quantum physics. Then, this is a bit a longer stretch, quantum physiology, and that speaks to the metabolism. You know, so I mentioned to you that one of the key aspects of living systems that differs them from non-living systems is, I would say, deliberate movement, free will, if you want to be philosophical. Another one is metabolism. That is, living systems cannot be living without constant input of energy through nutrients, or like bacteria or plants, photosynthesis, light, energy input is essential. So they call it metabolism, transformation of energy, energy transduction. And I'll show you at the end of next week that metabolism, which is the cornerstone of life, is quantum. So the most important process in living systems are two. First, cognition or processing of information, and the second, metabolism, are quantum processes. Everything else may be classical. I'm not saying that there are classical systems or classical laws in effect for living systems. If I grab a hammer and hit your, I'm not going to do that. That'll be a classical effect with quantum consequences, of course, loss of consciousness. But yeah, by and large, a lot of things are explained classically, but not some of the deepest, the most profound. Okay, and then we have quantum biology, which kind of overlaps with physiology. Here we'll have to go into the weeds, so to speak, and look at some biological structure and function, the composition of living cells, and what in these cells can be actually performing quantum functions or undergoing quantum effects. And then, of course, this quantum computing, quantum cryptography is an emerging field. I will not speak about this. I'm just giving you something that you can read in newspapers even these days, because quantum physics allows us to do things that were not really doable before. Cryptography is one of those, because if you have a quantum code or encode something in terms of quantum states, then without the proper key to read it, you would destroy the quantum state, and that's gone. You can never break the code by eavesdropping on a quantum system. I mean, that's one of those things. And then, yeah, once again, quantum brain. Why do I single out anesthesiology? Because this is one of the mysteries too, unexplained. Anesthesia is really, I mean, yes, I know that anesthesiologists will tell me, yeah, we know how it works, but really not. At the molecular level, nobody knows. But at the level of, some receptors are inhibited, some are blocked, and nuclear membrane, neuronal membranes, rather. I know that, but there are exceptions, and things like xenon, a single atom, is an anesthetic. How does it work? Nobody knows. So there are always exceptions. There are some empirical laws, but okay. As a physicist, I would say these are not explanations of the mechanism per se. I have a very good friend who is three actually, anesthesiologists, and they are very skeptical about this. One of whom is a professor at Stanford, and he came up with a very interesting single liner about anesthesiology. He said, all the mechanisms are sufficient but not necessary. So there are many. So there are many explanations. So different mechanisms. People say, oh, this is lipid composition of the membrane. This is the receptor blocking. This is, yeah, it may be sufficient but not necessary, because we have another example that shows it doesn't happen. Right? That's sufficient but not necessary. So in a single sentence, we don't know for sure what it is. But what do? They all turn off consciousness. I mean, if consciousness is a quantum state, as many people, including Penrose, claim, then they interfere with the quantum state. Think about this. This is amazing. So a single atom like xenon may be doing something to the state of the entire brain of a person under anesthesia. How is this possible? And as some of you may know, we believe that, let's say, memory and and cognition, information processing is through synaptic connections, activation, deactivation of neurons, action potentials, all of this. Action potentials still propagate in the brains of patients under anesthesia. So it's not that they were switching off action potentials, we're not. But, as far as I know, we're slowing them down a bit. Maybe there's something critical. Okay, so quantum anesthesiology, question mark, we don't know. And then I mentioned, and I will just move on, quantum psychology, psychiatry. I was invited actually to a special session at the American Association of Psychiatrists in San Francisco a few years ago. And with a colleague of mine who is a psychiatrist from Yale, we gave a session on quantum physics. Is quantum physics useful for psychiatry? And we got a full house. It was very well attended and lots of questions. So I think there is a ripe moment for these ideas to percolate to this field as well. So before I tell you what quantum physics is all about, I want to tell you what physics was about before quantum phenomena were discovered. So basically there are four major building blocks that created this huge field of physics. The first one, everybody here probably knows, is classical mechanics. So mechanics, we have the simple machines, levers and so on. But it can be very complicated, by the way. And Sir Isaac Newton, one of the greatest thinkers of all time, came up with Newton's laws, which still are valid today, and if you ask an engineer, he will say, very useful indeed. And then other people made it more mathematical, elegant, and beautiful. It's really a fantastic field. Lagrange, Hamilton's equations. And I'll just give you one snippet of forward thinking, that these elegant mathematical formulations of classical mechanics, not Newton's laws are very simple, F equals ma, okay, it's not beautiful, it's just a linear relationship. But Hamilton's equations and Lagrange's equations are beautiful, symmetrical. They actually, if you replace them with quantum variables, they are valid in quantum mechanics, which is also phenomenal, that there is a direct translation. It's like if you had the Rosetta Stone of science, of physics. This is classical language, this is quantum language. And you can translate from classical to quantum by replacing things like force, momentum, or velocity with quantum equivalent variables. But the equations look the same. Okay, so that's the first block. The second block is electricity and magnetism, which were combined into electromagnetism by James Clerk Maxwell, a great Scottish physicist. I was once invited to give a talk at the Royal Society in London, and I was very humbled to speak there. There were portraits of Maxwell and Newton on the walls looking at me sternly like, what the hell are you doing here?
Watch yourself.
Watch yourself. So anyway, that's also, Maxwell's equations are, again, so mathematical beauty in physics speaks of the truth. Some people say mathematics is the language of truth. If something is ugly, it's probably not true. In physics, I'm not extending it beyond physics. So these equations, Hamilton equations and Maxwell's equations are beautifully compact and symmetrical. So symmetry is an expression of beauty in some sense. Right? So they explain to us how electrical charges and currents and magnetic fields interact. And so that leads to many of the technological advances of 20th. So this was second. Third is thermodynamics, which was developed in 19th century, specifically early 19th century, by people like Watt, Carnot, Thomson, Clausius, and the first great American physicist, Gibbs, I think it's John Willard Gibbs was his full name, Gibbs free energy, thermodynamics. And so that gave rise to the first industrial revolution. heat engines, machines that were, combustion engines, and so on, were constructed on the basis of the knowledge of thermodynamics. This was the second industrial revolution: electricity, electrical engines, communication, eventually, radio communication, electromagnetic waves, transmission. We don't have quantum mechanics yet, but that'll be third one is information revolution. So, and quantum revolution probably is around the corner. That is implementing quantum principles in information technology, quantum computing, and so on. So, this, and that, the third block, and the fourth one, just at the end of 19th century, statistical mechanics, which is quite different because it's how shall I put it? It applies to systems of many particles, just like statistics. You take public opinion polls, use statistics, and draw conclusions about the population based on not asking every single person what they think, but sampling. So statistical mechanics applies to systems, largely systems of identical particles, many, uncountable number of particles, and drawing conclusions about their states by averaging average properties. Averages, moments, statistical moments, variance, standard deviation, all that stuff. But it's very powerful. And Stefan Boltzmann was a tragic figure, one of the greatest geniuses in physics. He came up with these concepts, including the concept of entropy, which is so powerful even in living systems, and its mirror image information, channel information. He was misunderstood and committed suicide in the end by not being able to communicate his ideas and be accepted by the community. So that's sad, very sad. But he was a great scientist. Okay, so that was 1899. Now, in 1894, so 6 years before the revolution, this is a quote from Albert Michelson. Sometimes he's confused with Lord Kelvin. He stated, "It seems probable that most of the grand underlying principles have been firmly established. The future truths of physical science are to be looked in the 6th decimal place." That means the rest is just making tiny corrections. Everything is known, we know everything. In other words, physics is finished. Well, he couldn't have been more incorrect in this statement, because, as I said, almost 6 years later, everything collapsed. And these are the revolutions that occurred in the 20th century, starting with the special theory of relativity by Einstein, who basically dismissed time as an absolute quantity. It's actually not even a physical quantity. And then general theory of relativity in 1917, which dismisses space as something which is objective and absolute. And then we have quantum mechanics, which dismissed basically the concept of masses as such. So we don't have time, we don't have space, we don't have mass. Everything is fluid and subjective to some degree. That's why Deepak Chopra and philosophers are so gaga about modern physics, because you can spin it in many different ways. So quantum mechanics was born out of these unexplained experiments, but it was created by theoreticians. All of these people, Max Planck, Max Planck Institute now in Germany, some of the most prestigious scientific institutions in the world. Erwin Schrödinger, Werner Heisenberg, Paul Adrian Dirac, Wolfgang Pauli. These were the creators of modern physics, quantum physics. I want to make one comment, sociological comment, that in physics, because of these guys, and this guy especially, theoretical physics that I study, but that's immaterial, is highly respected. It's considered to be the highest level of intellectual pursuit in physics, theoretical physics. In biology, theoretical biology is considered to be kind of garbage science. Speculations, hypothetical, maybe, whatever. not serious. So there's a cultural gap when a theoretical physicist like me enters into the field of biology. I recognize eventually you have to do experiments to be considered seriously by other biologists. But hopefully there will be another Newton or Einstein in biology who will change that perception, because biology requires, in my opinion, some big thinkers, not just technicians who, even an army of technicians in the lab, painstakingly mixing and stirring and looking. There's more to it than that. Okay, so these were the scientific revolutions. Quantum chemistry followed, and now of course quantum field theory, which is, we will not talk about this because this is a more profound reincarnation of quantum physics into the realm of subatomic, what happens inside the atom and even the nucleus, subatomic particles, which for the purpose of this course and for all intents and purposes in biology, they don't matter at all. If we talk about electrons, yeah, because of chemical bonds, that's as far as we go. But we don't need to know quantum field theory, which is very esoteric. Nonetheless, you should know the name. And there are many Nobel Prizes given to quantum field theorists, including one person I need to mention, Richard Feynman, who was one of the greatest American physicists of the 20th century, got a Nobel Prize. Have you watched Oppenheimer? So you get my drift. Feynman is in the movie Oppenheimer did his PhD. He was an American who went to Germany to do his PhD, because at that time, that's another cultural shift. At that time, in around 1930s, 1940s, all of this quantum stuff was being developed in Europe, in Germany, Switzerland, Austria, German-speaking, and a little bit in England, and also Denmark, Niels Bohr. So you had to go to Europe to study. Now it's the opposite, right? You have to come to America to learn physics. Not quite that. Okay, then of course, then we have DNA, discovery of the structure of DNA, molecular level, and this is what I think allowed the convergence of physics and biology into biophysics. When biology acquired the tools to understand structures of proteins, DNA, complexes of proteins, enzymes, and now we are starting to build atomic resolution models of biological systems, including cells and beyond. And now we have a hint of quantum biology, maybe more than a hint. Okay, so that's basically where we are at. So I have 10 minutes. I will just say a few things about the timeline. Now we are getting into the nitty-gritty of quantum physics. So I'm sorry, but you have to focus now for about 10 minutes or less. So this is the timeline of what happened. 1900, Max Planck, who was actually, by the way, that's another sociological comment and a plea to you guys, you're young. He was the oldest of the group. He was 42 years old when he discovered the quantization rule. He was considered to be an old guy. Einstein, when he wrote his fundamental papers, I think he was 27 and up to 32 or something like that. So you have a few years left to make your major discoveries. So Einstein explained the photoelectric effect, for which he got a Nobel Prize. He should have been given 3 or 5 Nobel Prizes, but only one for this, I would say, the least fundamental discovery he made, but important. Niels Bohr, 1913, explained this is very important, the second group of experiments. There were very sharp emission and absorption lines, spectral lines, for atoms, including hydrogen and helium, which now is the basis of spectroscopy that allows us to see the composition of stars, distant stars, galaxies, and the amount of pollution in the air. All of this is because of that little observation that links the wavelength of the spectral line with the energy that we'll see is, according to Max Planck's formula, And that is related to the difference in the energy levels of atoms or molecules, whatever the case may be. So, amazing insights that didn't, occur before. And Louis de Broglie, Frenchman, he was actually a count, an aristocratic figure. I think he kind of dispensed with all the degrees, just went for the Nobel Prize. Just give me a Nobel Prize, don't bother with studying things. He wrote a thesis on the wave-particle duality. So, by the way, for the final exam here, this is one of the most important things. In classical physics, you have waves, ocean waves, acoustic waves, vibrations of molecules in the air, mechanical waves, and then particles, ping pong balls, golf balls, footballs, and so on. In quantum mechanics, according to Louis de Broglie, and we now know it was correct, quantum objects are both at the same time, depending on how you look at them and what you try to determine, whether they are diffracting through slits, then a particle like an electron or proton will behave like a wave. It will go through all the slits. Or if they are colliding like a photon, so it's a quantum of light, strikes a stationary particle and will collide with it as if photon was a particle. And by the way, Sir Isaac Newton, 300 or 50 years before, claimed that light is composed of particles. So he was visionary in this sense, didn't understand quantum mechanics, of course, because nobody did. But anyway, so that's Louis de Broglie, the complement duality, the wave-particle duality. And then 1925 is the year where quantum physics became formalized or formulated mathematically properly, moved away from classical concept completely by these two gentlemen, Werner Heisenberg, who was a German, I think at Göttingen, and Oppenheimer went to Göttingen to study, and Werner Schrödinger, and Erwin Schrödinger, who was Austrian, and later on we'll see him again. He wrote a book, What is Life, in 1944. After he got his Nobel Prize in physics, he probably wanted to get a Nobel Prize in medicine, but wrote this amazing book, still interesting today. They developed these mathematical formulations of quantum physics. One is in terms of operators, and the other, Schrödinger, in terms of wave functions, psi. We started with the psi, it's Schrödinger here. And then this is another important philosophical insight. So you may know that in the 17th century, especially French physicists and scientists came up with this concept of determinism. And till today, we kind of feel that the world operates deterministically. That means there's a cause and effect in some kind of proportionality. You can predict development and evolution of systems. So Simon de Laplace, one of those major figures in French determinism, he came up with this idea that he said, if you give me the initial conditions of all the particles in the universe, I'll predict the future at any point in the future. Which today we would say, if I were British, I would say bollocks. Nonsense. Even a single particle cannot be predicted. Even a single electron cannot be predicted in terms of its evolution because of the Heisenberg uncertainty principle. So Werner Heisenberg showed that according to quantum mechanics, any two properties which are so-called complementary, again, I will not get into what that means specifically, but for example, position of a particle and its velocity or momentum cannot be simultaneously known, even for a single particle. You can know one and lose all information about the other, or vice versa, but you cannot know both with arbitrary precision. So determinism is out. So philosophically, this is important. That means even if a single particle cannot be predicted completely, then what about the rest of the world? We'll come to this because it's the borderline between philosophy and science. Dirac introduced this unified quantum mechanics with Einstein's relativity. So he basically formulated quantum physics for what does it mean relativistic particles. It means particles that will be moving very fast, close to the speed of light, because normal or quantum mechanics would not apply to them, only applies to very slow moving objects. You have to combine this, previous slide, with special theory of relativity, and that has been done. But what hasn't been done, everything has been done except one thing. Nobody has been able to combine quantum physics with gravity. That's the missing link. And there's some very interesting comments about this. There's a very beautiful YouTube video of Freeman Dyson, who talks about this, and he dismisses this as a non-issue. That it doesn't, we should not strive to unify everything because they are at completely different scales. Okay, so John von Neumann, you may have heard about him. He basically provided the basis of computer science. He also developed rigorous mathematical formulation of quantum mechanics. And then these guys, I mentioned Feynman, Schwinger, and Tomonaga, introduced quantum field theory to explain electrodynamics. So Maxwell's theorem, remember the fourth block, no, the second block, Maxwell and other gentlemen, electromagnetism, classical electromagnetism, now quantized by these people, quantum electrodynamics, QED. So, great legacy. And great characters, like if you watched Oppenheimer, 3 hours and a bit, I think, captivating movie, and I think for the first time physicists were shown as colorful, interesting characters. And if I have time and strength, I would like to write a book about this cast of characters. All of them were very interesting people. So I'll end with a picture, which this is a photo of these cast of characters, including Einstein, Marie Curie, Max Planck, and many others, Schrödinger, Heisenberg, Pauli, from these conferences in Brussels, organized by a chemical company, Solvay, and these conferences, almost everybody in this photo had got a Nobel Prize. These conferences solidified the foundations of quantum mechanics, and that then unleashed everything. So this was, thank you, this was very chatty, I think, a very descriptive storytelling, but maybe you need it.
Very interesting. Thank you.
Thank you.
Yeah.
And I'm on slide 13 of 150.